Hi, good evening and welcome to the Institute of Physics Yorkshire Branch Lecture Series. I'm Andy Parr and I run the Science Outreach Programme here in York. Amongst other activities, I organise some physics lectures as part of IOP Yorkshire Branch, and we are here online tonight. I gather there's a really good number of you out there in the audience, so fantastic and welcome again. We're looking forward to our lecture this evening all about galaxies with Carolyn Crawford. We also have Bethany Wotton, who's also from the IOP, joining us, helping out behind the scenes. There's a bit of housekeeping, which is that because this is a Zoom webinar, your audio and video won't be visible to anyone. So there's no way you can accidentally appear on the screen or have your audio heard. If you have a question for Carolyn, just type it in the Q&A box and we'll try and get to them at the end of the talk. There is also a chat box where you can message us during the webinar should you need any assistance. And it'd be good to hear from you in the Q&A. Finally, this lecture is being recorded and it will be uploaded to the IOP Yorkshire Region and Nation section of YouTube on the YouTube channel, so you can enjoy it in the future as well. So to introduce the speaker this evening, I'm delighted to introduce Carolyn Crawford, who studied maths as an undergraduate and then completed a PhD in astronomy, both at Cambridge University. She went on to a series of fellowships, mainly at Cambridge University, and was most recently a fellow and lecturer at Emmanuel College. Her successful career in astronomy research has yielded a great number of research papers, many which concentrated on galaxy clusters and also the influence of supermassive black holes on galaxies. Later in her career, she has been heavily involved in public outreach and has made many media appearances on TV and radio. Between 2011 and 2015, she was the prestigious Gresham Professor of Astronomy. Carolyn also ran the outreach programme at Cambridge University, the Cambridge Institute of Astronomy. And Carolyn really is one of the UK's foremost science communicators. She visited us here in New York a few years ago at St. Peter's and gave a fantastic talk about nebulae, and it's really brilliant that she's sort of joining us, albeit online, for a talk in York again. And that talk was one of probably approaching 1,000 public lectures that she's given over the years, so many hundreds at least. And so yes, really looking forward to her speaking. So this evening's talk by Carolyn is entitled The Universe of Galaxies. Again, we'd love you to get involved and put questions in the Q&A box. So yeah, do so, and we'll deal with that at the end of the talk. So without further ado, can I pass you over to Carolyn for this evening's talk?
Thank you, Andy, for that lovely introduction. So if you just all bear with me, I shall try and share my presentation. This is the kind of thing that always goes well in practice, but during the actual talk, Right, I'm assuming you can all see my screen clearly enough, though do kind of wave at me, tell me if not. So this evening's talk, I've just called it A Universe of Galaxies because that's what we live in. We live in a galaxy, which is one of just perhaps 120 billion up to a trillion galaxies out there, probably upward of that. And we know roughly how many galaxies there are because we've counted them, not every single one. But here, for example, is what has been one of the deepest visible images of the sky. And every blob, just about every blob you see in there are a couple of stars. There's one there, there's one down there. You can tell them because they've got the diffraction spikes in them. But there are about 10,000 galaxies in this image. And this image covers a patch of sky that's, it's the same angle that if you held a single grain of sugar at arm's length, that's about the size of the sky that it covers. So here you can see that if that is representative of the whole sky, that's where we get numbers of hundreds of billions, if not trillions of galaxies out there. And they range in the number of stars they hold. You get from several million stars up to several trillion stars. And they range in size. You get small dwarf galaxies that are maybe only thousands of light years across, large spirals like our own, which is about 120,000 light years across. Remember, 1 light year is 9.5 million kilometers. I mean, these are just impossibly large numbers. And there are even giant elliptical galaxies, which can be 500,000 light years across. And the masses of individual galaxies, when you weigh up all the gas and the stars and the dark matter in them, range from a few million to up to 100 trillion times the mass of just our sun on its own. So there's enormous variation. In terms of their color, there is some variation in color. It depends on what's going on in the galaxy, whether there's star formation or not, what kind of stars are in the galaxy, what kind of gas is in the galaxy. And also morphology tells you something about the history of the galaxy. And I'm going to talk you through the ranges of all of those. But to start up with, let's go close to home. And the galaxy we're perhaps most familiar with, the kind that fills all your coffee table astronomy books, the Spyro Galaxies. And these aren't necessarily the most common kinds of galaxies, but the ones that everybody likes to take pictures of because they are so beautiful. Yes, if I'm out with my telescope, I will go look at a Spyro Galaxies. They're my first choice because they are stunning. And how they present to us and how they look depends very much on their orientation. Now, Spyro Galaxy is a sort of flat frisbee shape. And here you see a frisbee, the face on, and you see all the stars in the galaxy. But sometimes that frisbee is climbed at a slight angle to you. And you get it looks much more flattened. It's just that it's tilted at an angle to you. And then occasionally you get ones like over here on the right that are edge on. And here's an edge on galaxy. And this very much gives you the sense of the structure within that frisbee. You've got a large ball of stars in the middle, and then a flat disk surrounding it. And the analogy tends to be like 2 fried eggs stuck back to back. And you've got the egg yolk in the center, and then you've got the egg white stretching out. And if this is our galaxy, we live about halfway out from the center to the edge in this flat disk. And you can see this flat disk looks dark because there isn't just stars there. There's dust, opaque dust. I talked about this in my nebulae talk. It's just solid particles of like soot and sand that are absolutely tiny. But when you have clouds light years long, they block out the light from the background stars. They seem to sort of cut the galaxy in half. And indeed, remember, if we live in the disk and we look into our galaxy, this is the kind of view we see. We are looking along the plane of the disk towards the center. So compare this edge-on galaxy to the view of the night sky from Earth, okay, admittedly not from Cambridge and not from York. This is from New Zealand, where you're looking towards from the southern hemisphere, you look towards more the center of the galaxy. But you get the same sense of a bulge of stars here, and then a flat disk lie across the sky, forming the band of the Milky Way. And if you get a really dark night, you can see these dust clouds that are embedded amongst the stars in the disk. So you have different orientations, give you different impressions of Sparrow Galaxies. When you look at them face on, you can see these dust lanes. Now, these dark bands that swirl around, these are not absences of stars. Those are those dust clouds blocking the stars. You also see a difference in colors. The stars in the disk, the flat disk, are blue, and blue stars are massive stars. They're young stars. That's telling you that the disk of the galaxy is where stars are being born. That's an active region of star formation. And the other clue we have about that are these pink blotches, which are the nebulae. Those are regions of active star formation going on. So you can tell when a galaxy is actively forming stars because it is blue and it has lots of pink nebulae, and it often has all these sort of compressed dust lanes where the gas clouds are being compressed. Now remember that because you need that in the future. The center of the galaxy here is white because that is older stars. It's less disturbed. All the sort of activities going on out in the disk. And this is just a picture of, in our galaxy, one of those nearby nebulae. This is a gas cloud, and these nebulae are pink because The stars are forming from the gas that lies between the stars. We call this the interstellar medium, and it's mostly hydrogen. And if you excite hydrogen by throwing lots of energetic photons at it, it glows this characteristic pink color. So those pink blobs are where the gas is being heated up. Throughout the stars and the disk, there's also cold gas, neutral gas, carbon monoxide, hydrogen molecules that are so cold that we would need a radio dish or radio telescope to actually observe them. So you have your constituents of the galaxy. You've got the young star formation, you've got the dust, you've got the nebulae. I'm telling you, there's also cold gas. I mean, I can show you pictures of cold gas, but it's sort of contour plots and they're not as pretty as the visible images. But in between all of this, there's a flat disk of cold gas. Just have to imagine it there. And the whole system is rotating. So Spyro Galaxies are rotating. And our own galaxy, the Milky Way, is rotating at about 220 kilometers per second. So remember that you're not just on a planet that's going around the sun, but that sun is also going around the center of the galaxy at phenomenal speed. And even at that speed of like 220 kilometers per second, we only go around the galaxy once about every 240 million years. So that means since the sun was born about 4.5 billion years ago, we've only gone around the galaxy just short of 20 times. You know, we are fairly recent newcomers within our universe. So this rotation tells you one of the fundamental things about a galaxy. Here we've got Spyro Galaxy face on. This is all rotating. I hope you get the sense that it's actually rotating in a clockwise direction. The spiral arm direction tells you which way it's rotating. Now, we can use this rotation to weigh the galaxy. Now, if the galaxy wasn't there and you had a star in the disk, if there isn't anything else around, it's minding its own business, it's happily going through space. But if it is near a galaxy, you have a gravitational pull to all the mass that's within the galaxy with sort of inner radius. And that pulls the star towards the center of the galaxy. Now, it doesn't put it to the center, it just diverges it slightly and it tugs it round. And so in the same way, a satellite falls by gravity around the Earth, a star, any of the stars in the disk are just falling due to gravity and deflected around in an orbit. And what we can do is we can measure how fast the stars are going around the center of the galaxy because they're responding to a gravitational potential. That's what's making them do this rotational motion, is the gravitational potential of the galaxy, which is related to how massive the galaxy is. So if you can measure, say, an average speed for all the stars going around the galaxy, you get an idea of what mass they're responding to. Now, when we do this in our solar system, it's easy. You have 99.9 whatever % of the mass of our solar system is contained within the sun. And then the planets orbit around it. And you just have a very sharp drop off in orbital velocity with distance away from the sun. If all the mass was concentrated at the center of the galaxy, this is what we'd expect to see. So plotting, we've got radius against orbital or rotational velocity on the y-axis. This is, if you just looked at the distribution of the stars, I told you, you've got that big bulge of stars in the center. Most of the mass of stars is right at the center of the galaxy. If you just thought all the mass was contained within those stars, you'd expect this kind of curve so that the velocity of the stars would drop off with distance away from the center of the galaxy. And it's not just stars, you could measure the amount of gas that's there, cold gas, warm gas, add that all in, you'd still get a similar effect. However, what we measure is the stars are going too fast. Even our own sun, which is about here, is going about 75 kilometers per second too fast. If it was just responding to all the mass that we see in the stars and the gas in the galaxy, that means that there has to be an extra gravitational component. And it is this that was some of the primary evidence for a dark matter halo. So if we add, okay, say if we add in the gas, it's not enough. mathematically, when you do the modeling for our galaxy, for just about every big spiral galaxy you see out there, you can only match the observed profile of the rotational velocity of distance if you have a large component of matter at large radii from the center of the galaxy. And this is something we don't observe directly, but we detect it's there by its gravitational pull. And this is the dark matter. There's other evidence for dark matter from clusters of galaxies, from motions of stars in the elliptical galaxy. But this is the original dark matter evidence now for spiral galaxies. And the thing about the dark matter, even though we don't detect it directly, the reason it's called dark matter is because it doesn't interact with light in any way. We only detect its influence by the way gravitation interacts with things that do emit light. And it is vast. So if you have a normal galaxy, Spyro Galaxy, you've probably got about at least 10 times the mass that's in the stars and the hot gas and the cold gas in the galaxy in the dark matter. And not just that, it extends out to much greater radii. So you get 10 times the mass, and it probably goes out to 10 times the distance from the center of the galaxy. It's much more extended. So with any galaxy, whether it's a large elliptical or a spiral like this, it is the dark matter that's holding the galaxy together, not the stars and the gas that we see, the pretty stuff, but it's this invisible mass that we only detect by its gravitation. That's a key thing we learn from galaxies that we would not know otherwise, that actually most of the matter in the universe is in the form of this dark matter. The other thing that we can learn about a galaxy that we can't observe directly is from a similar sort of process, but looking right at the center of the galaxy. So here are just some numbers, say for a typical Sparrow Galaxy. So say 10 times as much gas in the total mass, I suppose, sorry, 10 times as much mass in the total gravitating mass of the stuff you can see in any waveband, you know, whether it's infrared, optical, X-ray, visible. Now, this similar idea of detecting things by their gravitational pull also serves us well for the center of the galaxy. Now, this is an edge-on view of our galaxy. And if we zoom in with telescopes right to the center of the bulge, well, first of all, we have to use infrared telescopes. We can only see through the dust if we use infrared light because it kind of hops over the dust particles because it's longer wavelength. So as we go into the center of the galaxy, it gets more and more complex. We're looking in infrared light now. Right at the center of the galaxy, there is a cluster of stars. And astronomers have been observing the very core stars for a number of years. And those stars are moving. Here's just in lurid false color images, several, sort of probably about 20 years worth of tracking the orbits of these stars. And each of these purple sort of false color blobs is one of the stars. And you can see the one with the yellow orbit has already made a circuit. Now, all these stars are moving and they're in orbit around something. And we can measure, again, we can measure how fast they're moving. Obviously, it's a three-dimensional situation. There's lots of stars we can track. But by seeing the speed at which they're going around and measuring sort of how far they are away from whatever they're circling around, we can weigh what they're in orbit around. And there's a mass that is 4 million solar masses. Now, that's not a problem. 4 million solar masses is easy. You know, that's we've got galaxies that are trillions of solar masses. The problem is that you have to compress all those 4 million solar masses into a region that's about the diameter of our solar system. And not just that, but it is actually invisible. And this is the primary evidence we have for a supermassive black hole at the center of our galaxy. So 4 million solar masses that is invisible. It is not actively accreting. This is what we call a dormant black hole. It's obviously eaten dust and gas and stars in the past, maybe even perhaps snacking on a few gas clouds or stars at the minute. But it's eaten everything in its vicinity, and these stars are far enough away that it'll get sucked onto the black hole. They're just in orbit around it. But this is how we know it's there. And we can do a similar analysis with other galaxies. Look, it's more difficult when they're further away, but we could look at other things in orbit around the center of the galaxy. I'll come back to the black holes in a bit because they're part of the story of galaxies. But just to remind you about morphologies, this is just an artist's impression. If we were able to move it out of the disk of our galaxy and look back down, this is what we think our galaxy would look like. It's not one of those neat, completely sort of neat spirals. It actually has an extended bar in the center. And barred spirals are not uncommon. You have a full range of Spyro Galaxies. You can see here you have ones in the top left where there's a large bulge at the center, or ones on the right where you have very loose, fluffy spiral arms and a tiny bulge, or you've got ones which are very tightly wound on the left. And so there's a whole variety of subtleties about Spyro Galaxy morphology. The other main type of galaxy we have, so here you've got a tight spiral and a fluffy spiral, but these are dwarfed by a giant elliptical galaxy. And the giant ellipticals live up to their name. These really are the largest galaxies around, the most massive as well as the largest. Our galaxy in comparison to this would be equivalent to one of these little blurs that you have in the background. And these, again, go up to trillions of solar masses in mass. You will see they look very different. They don't have the structure. They're very white or yellow. They don't have active star formation. Elliptical galaxies have lots of hot gas. We can look at these in X-rays, and we can see gas at millions of degrees in the gravitational potential of the galaxy. But in terms of the stars, there's not enough cold gas. There aren't young stars forming. So there's a lack of star formation. They look the same, whichever way you look at them. They're shaped like a rugby ball or a football. And if you've got a football or rugby ball, well, maybe it's sort of slightly less squashed or slightly elongated, but they're the same basic shape. They're the same basic elliptical galaxy. And these have, again, just as much dark matter. We measure it in different ways. We maybe look at the motions of the stars or the globular clusters around the center of the galaxy that, again, responding to the gravity of the whole galaxy or what's going on right in the core. And then you have really weird galaxies. These are ones that don't quite fit the description of the spiral elliptical. Now, here's one where you can see an elliptical galaxy and something that looks very like it used to be a spiral galaxy in between that and another very blue galaxy. And this is when galaxies get too close to each other. Now, I know the universe is expanding, everything's moving away from each other. And that's true generically about the whole universe. But there are regions where you have galaxies that are close enough together that their mutual gravity overwhelms the expansion of the universe and they move or respond to each other's gravity. And they can get pulled together by their mutual gravitational pull and then pulled apart into these amazing shapes. And these are called interacting galaxies. And they're relatively rare in the nearby universe. We see this in our own galaxy. Here again is the Milky Way along the line of the sky. And if in the southern hemisphere, you look in the sky, you can see two little clouds. These are the Magellanic Clouds, which reflect two small galaxies, each about 100th the mass of our galaxy, that are orbiting the Milky Way every kind of 2 billion years. One's about 170,000 light years away, one's about 200,000 light years away. So they're out beyond the disk. But they're little dwarf galaxies that are just tied gravitationally to our galaxy. And if you look at them in more detail, what I hope you notice is they don't have a regular morphology. They've got lots of blue stars. They've got lots of pink nebulae. There's lots of active star formation. And this is a characteristic of what happens when you start pulling galaxies apart under gravity. Gravity pulls and it also compresses. And if you compress gas clouds, you trigger star formation to occur. So vigorous star formation is a sign perhaps of interactions between galaxies. You can also tell it's interesting with these two little things that they are being completely destroyed by our galaxy. Here again, it's just the whole sky, and you have our galaxy along the center. The two little Magellanic Clouds are down here. This is a visible image, but if we were to take this image and look in the radio wave band, remember radio wave band looks at neutral gas, hydrogen, carbon monoxide, sort of molecules of stuff that's in between the stars. What you find is there's a stream, and all of this gas is just being pulled out and left in these galaxies' wake. They're just slowly being pulled to shreds and unraveled by the mass of our galaxy. So this is a very strong effect because these are tiny galaxies and they're quite close to very massive galaxies. So it's kind of destroying them. These are not the only galaxies we have around us. I don't know if you can see, if this is our Milky Way, here's just a list of some of the small dwarf galaxies. They're probably about 25 or 30, so round our Milky Way. And we're all part of something called the local group, where there are perhaps about 50 or more galaxies contained within a few 5 to 10 million light years across. So we don't just have our Milky galaxies, but there are two other large spirals. There's the Andromeda Galaxy over here, which if you are very lucky on a dark night over winter, you can see with the unaided eye. It's the only galaxy you can do that outside of our own. And the Triangulum Galaxy, and they're both Sparrow Galaxies. And this Andromeda Galaxy is a galaxy, it's kind of like the Milky Way's twin. It's a spiral galaxy, large spiral galaxy. You can see it's even got a couple of dwarf galaxies in orbit around it. And this is 2.5 million light years away. So each galaxy is about 120,000 light years across. They're separated by 2.5 million light years. However, that is still close enough that they can feel, Milky Way and Andromeda feel each other's gravity. So not only on a planet that's going around a star, that's going around the galaxy, but that galaxy is moving at very rapid speed towards space, towards Andromeda. And the two are being gradually pulled together. And we reckon in about 6 billion years, the two will collide. Now, astronomers are impatient. We like to know what's going to happen when you smash two galaxies together. I'll show you some images of this in action, but a simulation here, we'll start off with our Milky Way, and obviously we haven't got 6 billion years to watch a simulation, so this is sped up, so there's a ticker tape down at the bottom left telling you the time it's passing. Now remember, our Milky Way is spiraling round once every 240 million years. You are out one of these stars circling in the disk around it. We're now going to pan out and you see Andromeda coming in at the bottom right. So even though we're 2.5 million light years apart, it takes us a while to get close to each other. And watch, we don't just sort of crash together and that's it. It's a several processes. See this first pass, what happens that some tails of stars and gas are thrown out. And the two galaxies separate, but then gravity is going to pull them back again for a second encounter, and then maybe a third, and gradually the two will have merged to form a new system. Whether, I mean, who knows what happens to the sun and the Earth during this kind of collision? If you could view this from the Earth, here's a sort of fanciful artist's impression of the Andromeda Galaxy coming ever closer. But here you can see a stimulus of star formation and nebulae before the whole thing finally settles and you're left with older stars and less of the morphology. Now that's just a simulation, but we see this happening. Here's just a clip from that simulation. Compare this snapshot to two galaxies out there, two Sparrow Galaxies interacting with each other. So it's all happening too slowly for us to actually see them merging, but we see these sort of after effects and really dramatic examples of different stages in those merging processes, but they're very characterized by blue stars and blobby morphologies. And here's just again, two Spyro Galaxies that have merged. Spyro Galaxies are most useful for tracking interactions because they're very extended, and you've got this cold gas disk, and it can trigger the star formation. It's very easy to see when a Spyro Galaxy is disturbed. It's less easy to see whether an elliptical galaxy is disturbed. The elliptical galaxies do merge and do pull apart Spyro Galaxies. Here is an unusual elliptical galaxy. We think it has swallowed or is swallowing a Spyro Galaxy. So it's got these dust lanes, which you don't associate with elliptical galaxies that have been pulled, you know, maybe the shreds of the Spyro Galaxy that has merged with it. But this galaxy is interesting for another reason. It's relatively nearby in the constellation Centaurus. And if we looked at it in the radio wave band, oh, well, okay, let's just zoom in with HST. You can see how beautifully complicated all this region of star formation and what have you is due to the collision. But if we look in the radio wave band, it has two jets that come out from the center. So this is a composite where you've added radio jets to the visible image. And this gives us a sense that something important is happening at the center of this galaxy. And we know what sits at the center of the galaxy, of course, and that's your supermassive black hole. Now, I want to stress every big galaxy has a supermassive black hole at its core. Bigger the galaxy, the bigger supermassive black hole. One at the center of the Milky Way, most of the nearby galaxies is dormant, but every so often you get one that is still actively accreting. And one of the manifestations of this is that not all the material goes down the black hole, but some is wound out and expelled along huge jets that plow out of the galaxy and into the space out beyond the galaxy. So when you see a galaxy with radio jets, it's indicating of an active galactic nucleus, an actively accreting black hole right at the core. Here's just one of those giant ellipticals. This is what you have in the radio. The dot is the accretion, the activity around the central black hole. The jets show you the power of the material that's being blasted out, and then just a superposition of the two. So that tells you when these are actively accreting. And of course, one very famous example from the last few years that you may have heard about is M87. Giant elliptical, our nearest giant elliptical, it's 55 million light years away from us. In the visible, you can see there is a jet, this jet behavior that's out in the radio waveband tracks right down to the core of the galaxy. And indeed, if we look right with the Hubble Space Telescope, right at the material at the bottom of the jet that's going around the core of the galaxy, some of it is coming towards us, some of it is going away from us. So 60 light years either side of the center. Some is approaching at 500 kilometers per second, some's going away at 500 kilometers per second. That indicates a black hole of about 6 billion, so 6,000 million black holes. 6,000 billion solar masses at its core. And indeed, this is the black hole that was the topic of the recent picture of the event horizon. Well, the shadow of it's not really the event horizon, but it's a shadow of the black hole. And the light here shows you material that's being accreted down onto the central black hole. And it's part of the magnetic, this is just like a sea of charged plasmas, of charged particles, magnetic fields all swirling around at high velocity, responding to the gravity of that supermassive black hole. And part of that sort of vortex is the stirring up and propelling outwards of the jets. Okay, so that is a nearby black hole. If you go further back, so remember with galaxies, if you look at galaxies that are far away, the light has taken, so if galaxies sort of 30 million light years away from us, that means we're seeing as it was 30 million light years ago. Rather 30 million years ago, and the light's taken 30 million years to get to us. Now, that probably won't look very different from the nearby universe, but as soon as you start getting to perhaps 1 billion, 2 billion light years away, you're seeing back in time, you're seeing that galaxy as it was 1 or 2 billion years ago. So when we start looking at galaxies in the past, we have more of these active black holes than we have dormant ones in the nearby universe. So here perhaps is a nearby galaxy, Sparrow Galaxy, false colors, with a fairly active nucleus. If you have a really active black hole, one of those ones producing radio jets, perhaps even at higher power, it can outshine the entire galaxy. And the thing that is interesting is that it's matter falling under the gravitational potential. It's not totally efficient. If you put a 10% efficiency factor, so E equals 10% of MC squared available, you only need about 1 solar mass a year being accreted onto a supermassive black hole to power some of these really luminous quasars, they're called, short for quasi-stellar objects, because they look like stars until people could resolve the host galaxies underneath. And these are very common in the earlier universe. If we plot the number of these quasars with volume density, so here we've got the age of the universe across the x-axis, where the universe starts right at the left with the Big Bang, and it's just scaled to you are here where it's 1. Ignore the numbers, it's just sort of fractions of the universe. Now, if we go back in time to perhaps when the universe was, perhaps a third its current age, what we find, so we're going back perhaps say 10 billion years, quasars were about 1,000 times more common than they are in the nearby universe. So this is an evolutionary phase that we think all galaxies go through, and we know they all go through it because all the current universe, all those reasonably sized galaxies have supermassive black holes at their core. They're now dormant, but those will have grown by accreting matter, which means that the galaxy will have gone through an active phase in its past. So galaxies have evolved and changed through time. So this is giving us clues to the kind of history and how galaxies form and change. Okay, so the interesting thing here is that if you were looking back 10 billion years, and we now even go back further than that, and we see quasars, we see active accreting black holes. From the luminosity output by the quasars, we can make a very good educated guess as the mass of the supermassive black holes at the core. And one of the things that is really quite interesting is that these are not tiny black holes at the center of large galaxies in the past. These are, these were already very massive black holes at the core of these young galaxies. So black holes have existed through time at the centers of these galaxies. And so they have been there all along. They're part of the galaxy formation process. Not just that, there's another very important clue, which is the mass of the black hole relates to the mass of the galaxy. So here's one of the most giant galaxies. There is one of these giant elliptical galaxies. And if we plot mass of the host galaxies, and in the case of a Spyro Galaxy, that's just like most of the mass in stars in the bulge, but the mass in the stars of the host galaxy against the mass of the central black hole, you can see there's quite a neat relation. And this tells you that there's some relation between the galaxy and its central black hole. The black hole knows about the size and the mass of the galaxy knows something about the black hole. And this ranges from other galaxies that are like 10,000 solar masses up to about 10 billion solar masses in weight. And for all of these, you have the supermassive black hole is about 0.3% of the mass in the stars of the galaxy. It's about 1,000th of the entire mass once you sort of wind in the wider dark matter. So there's a correlation between the two. So this tells you that the black hole and its surrounding host galaxy form together. They sort of have a symbiosis. And this is one of the really hot topics in current galactic research, is trying to understand the processes where the black hole can influence the development of its host galaxy, and the host galaxy can also limit the growth of the black hole, such that you end up with this very tight observed relation. Now, this is just an artist's impression, but one of the things that is thought is that if you have a very active black hole at the center, and it accretes lots of material, it produces a lot of energy. And that energy can heat up the surrounding gas. Remember, stars form from cold gas, not hot gas. And so it can heat up the surroundings and stifle the star formation, the building up of its host galaxy. Remember, the energy from the black hole, of course, it influences the immediate surroundings, but through these jets that carry and transport energy through the galaxy, even though it's just at the core of the galaxy, it does influence the whole galaxy, the energy that's produced at the core. So you have a system where if the black hole gets too active, it stifles star formation in the host galaxy. And it also blasts out the immediate environments of the black hole. So there's nothing there for it to accrete. And therefore it then calms down. And so we have what we call a feedback process, a feedback loop, where the black hole and the galaxy kind of regulate each other's formation. And excuse me. And this is something that we're both modeling on our computers, but also trying to get a handle on observationally by tracking black hole activity through time. Now, one of the ways that we do that we look through time, is we look deeper into space. As I say, the further away an object, the longer its light has taken to get to us, and therefore we're seeing it as it was further back in time. So the deeper in space we look, we're looking back in time, and we can see earlier galaxies. Now, I showed you this image, 10,000 galaxies, 4 stars, taken with the Hubble Space Telescope. Now, the larger galaxies in this image tend to be the nearer ones. Some of them are large in the image because they're actually intrinsically large galaxies. But here we're seeing ones that are perhaps about 6 million light years, 60 million light years away. The furthest one, which is a tiny red blob somewhere, I can't even point it out to you because it's too small. It's about 13.2 or something billion light years away. It's very early part of the universe. But when we look at nearby galaxies, these large ones, they've got a fairly regular morphology. If we go back to some of the earlier galaxies, so looking back in time, some of these ones have a much more blobby appearance. And so here you have an indication that merging, I told you about interacting galaxies and the way they pull stars apart, they trigger star formation. Well, maybe this also is part of the process. It's not just this feedback process within a galaxy, but those galaxies are themselves building up by the merging of merging galaxies, where condensations of galaxies will maybe emerge to form bigger systems. This is what we go when we look further back in time. We see that these kind of interactive galaxies are fairly rare in the nearby universe. They're about 25% of the galaxies by the time you get an appreciable age of the universe. The problem is that we're still, when we look back, and as deep as we look back with the Hubble Space Telescope, we are still seeing galaxies. Even if they're blobby like this in the process of merging, they're still galaxies. We're not seeing the first stages of galaxy formation. This is what we think maybe is happening. Hidden behind the top right is, the Big Bang perhaps, and then over a period of 13.8 billion years, you maybe have you have formation of the first galaxies, some kind of merging system that leads to these very sort of blobby structures, which are blue. They're very bright in the infrared, which means they're absorbing light, re-radiating the infrared, so they're very dusty. So we call these starburst galaxies. A lot of building up of the galaxies. That build up of the galaxies also allows the central black hole to trigger, to start accreting. And we go through a phase, in most galaxies, a quasar phase, where they're very active. That then dies down, becomes a much more regular galaxy without that active nucleus. Maybe there's, depending on its immediate environment, there's perhaps some continued merging of galaxies. There are all kinds of reasons why galaxies do not merge. Galaxies can sort of pull each other apart without ever actually merging. If they just get close to each other, they can influence each other. And you settle down to a much more quiescent system in the current universe. This is our kind of the timeline we put together. The problem, of course, is we can't see these early phases. If we look back to that picture that I showed you, the one I said got 10,000 galaxies in, deepest visible image from the Hubble Space Telescope, it's this, you know, so you are here, the start of the universe is over on the right-hand side. We are looking back in terms of the Hubble Deep Field to where there's still galaxies. We're not seeing the first stars. We're not seeing the first galaxies. We're not seeing that very early stage of galaxies forming. So this is, of course, one of the prime drivers between the next generation space telescope, the James Webb Space Telescope. There are many reasons for the James Webb Space Telescope. It's important for looking at planetary systems around stars within our galaxy. It's going to peer into the dusty centers of galaxies. Remember, it's got 100 times sensitivity. It's really got 10 times the sharpness of the Hubble Space Telescope. It's got a 6.5 meter mirror telescope made up of 18 hexagonal segments. It is going, and it works in the infrared. Because it works in the infrared, remember, you can see through dusty infrared. So we'll see inside all those dusty regions within galaxies, our own galaxy and other galaxies, where I said star formation is happening. So we'll see star formation happening. We'll be able to see planets round, exoplanets around other stars around galaxies. Those are primary reasons for looking in the infrared. But the other reason, of course, is that very distant galaxies are moving at high speed away from us. Their light is redshifted, and it's redshifted so far that it's all the sort of star formation and the interesting things which normally we would see in blue light in the nearby universe are shifted right out to the infrared. And the further away the galaxy, the more it's in the infrared. So this is an amazing telescope. You will know it was launched around Christmas last year. Again, artist's impression on the right. Remember, it's not in orbit around the Earth. It's 1.5 million kilometers away. It's in a certain space where this shield that you have here, that blocks out the heat and the light from the Earth and the sun. And that's necessary because the whole system has to be kept at minus 220 degrees. If it was any warmer, the whole telescope would glow in the infrared, and you wouldn't be able to see you wouldn't be able to pick up the infrared from the distant universe because the whole telescope would just be glowing in front of you. So it's got this massive sun shield, which it has successfully deployed, and that will protect it from the heat and light of the sun and enable it to do this very cool infrared astronomy. The important thing then is with this high redshift, if this is how far in blue the Hubble Space Telescope went back to, say, when the universe was 500 million years old, the point about the James Webb Space Telescope is that we should be able to go to when the universe was less than 200 million years after the Big Bang. And that's a crucial point where we think we will see these very first galaxies forming. We'll be able to see perhaps and try and weigh how much, what kind of black holes they've got at the center. Have they got the black holes at the center yet? How dusty are they? Is there active star formation going on? What are the masses of the components that are building up to the galaxy? This is what we're all really excited about, that we're going to be seeing this process of galaxy formation for perhaps the first time. We're not there yet, though. The data images, the science images, will start coming back from the telescope this summer. However, just over what they've been spending time doing is bringing the telescope to a focus. They deployed the sun shield, and then you've got 18 hexagonal mirrors, which each produce an image of a distant star or galaxy. And so this is the raw image you have from those 18 mirrors, and they've been working hard to bring them to 18 individual images, so focusing each hexagonal image. And then they've been working, and this image was just released yesterday, to bring it to a perfect single focus when you stack each of those individual images. And then the really exciting thing, which was just today released, so this is hot off NASA TV, is that this image here, this allows us to evaluate how successfully they've got it in focus. This is just 2,100 seconds, right? Hubble Space Telescope images typically are hours long, days long. This is 2,100 second image of from James Webb, which is just aligning the focusing on a nearby star. But look in the background, we've got little galaxies already. Here's a pair of interacting galaxies. And here we've got a comparison of a ground-based optical image on the left, and then the same patch of sky, the same galaxy seen just in this image from James Webb Space Telescope. So this has really whetted our appetite that we're really going to be able to do the science we want to do. And hopefully in a year's time, 2 years' time, we have to be patient. It takes time to get these images. We'll not be looking at pictures like this as the deepest views of the universe, but we're hoping perhaps images more like this. This is a simulation, I stress, but in the end, Fred, that we'll be seeing further back in time, seeing back to the early universe and seeing even more possibilities and variations and history in all the galaxies across the universe. So I'm very excited, and to keep an eye on the news for some of these developments as they occur. Okay, I'm going to stop sharing my screen now, and thank you very much.
Thank you so much, Karen. That was a really superb talk, and thanks for bringing us right up to date as well with that image from James Webb Telescope. Now, there have been a few questions popping up in the Q&A and also in the chat. So if you wouldn't mind, I'll just put some of those to you for a couple of minutes, and we'll try and address some of those questions. So there was a couple of questions around the idea of galaxies and how do we know that the Milky Way itself is a spiral galaxy, and how do we go about measuring the rate of rotation that we see?
We know it's a Sparrow Galaxy because we sort of map out the star distribution. I mean, William Herschel was doing this back in the 18th century, counting stars in different directions and showing that flat plane across the sky just looks, I mean, it's a comparison also to other galaxies. I will say our Milky Way is one of the more difficult galaxies to map because you've got all, you know, you're looking along the edge. It's like, say you were going to do a map of York. You'd be able to do a map of York excellently if you could fly above it and look down and you could see all the streets and everything. You're actually trying to do it because you're in the middle of York. You've got buildings and cars and roads and people in the way, and you've got to be able to see through them. So it is quite difficult to disentangle the structure of the Milky Way. But we do this by measuring stars. There's a satellite called Gaia that's been out in space for like the last 5 years that is just is surveying 1 billion stars in the galaxy and mapping out their movements, their colors, their distribution in space. So we can do it with stars. We can also look at the gas clouds in the galaxy and how they're rotating and how they're distributed. So it's not trivial. It's been a lot of the focus of the work, say, through the 20th century, you know, first half of the 20th century, was mapping out spiral arms of our galaxy. But with a bit of perseverance, you can do it. But you also learn by looking at other galaxies and making that analogy that there are so many other ones like this. What we see around us seems to map onto those other galaxies better.
Mm-hmm. Very good. There were a couple of questions relating to dark matter, which ones are more general about what is the density of dark matter, you know, in kilograms per meter cubed, but also, I guess, linked to that is sort of with regards to the dark matter cloud that we have or halo for a galaxy. So the question was the extent. So, regards to the dark matter, is the extent dependent on the properties of the dark matter particles themselves? And if so, is the dark matter cloud especially sensitive to those properties?
Okay, well, this is one of the things that, of course, left hanging, just mentioning dark matter in passing. I can tell you lots of things that dark matter isn't. It's not clouds of small black holes. It's not rocky planets. It's nothing that we call baryonic matter, which is stuff that will emit energy in some wave bands. If it's rock, it'll give off stuff in the infrared. It's not ordinary matter. It's got to be some kind of extraordinary matter. And one of the best contenders is something called WIMPs, or weakly interacting massive particles. And the reason we've come down to that as one of the candidates, because it's got to be some kind of substance that doesn't interact with the electromagnetic force. Okay, because it doesn't absorb, reflect, it doesn't have any interaction with light whatsoever, but it does react to the gravitational force because it produces gravitation. So it's got to have mass. It's got to be fairly slowly moving. It's not sort of massive neutrinos, because they whiz around at phenomenal speed, and the distribution of the dark matter, so this comes back to the question, would be much more blurred, and it wouldn't have sort of gravitated to form galaxies in the time of the history of the universe. It's got to be fairly slowly moving, so they've got to be relatively massive particles. They've got to be relatively massive, and they've got to be weakly interacting as well, just in terms of the kind of the nuclear force, the strong and the weak nuclear forces they do or do not react to. But we don't know what it is. I mean, talking about dark matter is a whole other talk. But it is distributed in line with the galaxy. So if it's a Sparrow Galaxy, it's a sort of flattened distribution. If it's an elliptical galaxy, it's much more of a sort of elliptical distribution. If it like in a cluster of galaxies, it kind of fills the space between the galaxies. It's the whole cluster has got dark matter in it. So it follows the baryonic matter roughly, but it's much more spread out. And those are the kind of things, and also looking at interactions of galaxies, because when you see two Spyro Galaxies interact with each other, they're not just interacting with the stars and the gas that you see, but they're moving through each other's dark matter halos. So it's a way of testing the extent and the mass, and if you like, the mass density of the dark matter by doing simulations, and can they produce the kind of snapshots we see in interacting galaxies out there.
Mm-hmm. Very good. There was a question about black holes in, I think essentially, do we think that every galaxy has a black hole? Is essentially where the question is. Okay,
so let's just be absolutely sure. I'm talking about I should have made this clear earlier. I'm talking supermassive black holes. So I'm not talking about black holes that form when a massive star goes supernova. Supermassive black holes just sit at the core of the galaxy. And any appreciably big galaxy, one that's over perhaps a few thousand solar masses, maybe 1 million solar masses, has a black hole at the core. So yes, they are widespread through all the galaxies. So if you look at something like a dwarf galaxy like Magellanic Clouds, probably they don't have a supermassive black hole at the core. And that's partly because maybe they're fairly recently formed, or they're being torn up. They haven't really got their act together to get that supermassive black hole at the core. But any kind of large gravitationally stable system has one right at its center.
Brilliant. So, sort of on the back of the idea about supermassive black holes, and I think to some extent you addressed that the question when you were speaking about, it's kind of a chicken and egg really question, is did the black hole create the galaxy, or did the galaxy create the black hole, and do you have any feel for that?
Well, this is the $1 million question. Everybody tended to assume that perhaps there was some condition when the galaxy is first forming, that maybe, when you have very early universe, it doesn't have many sort of elements other than hydrogen, that smattering of helium. Maybe you can form much bigger stars. There's some conditions of that, all this sort of stuff that's built up in stars. When you've got primordial gas, maybe you can build really massive stars, and maybe they merge together and form this sort of seed black hole at the center of the galaxy. And then that grows in symbiosis of the galaxy. But we don't know for sure. And it's worrying that when we look at some of these very distant quasars, very distant galaxies, we see a stonkingly big, you know, n billion solar mass black hole already in place. And that worries us. Okay, it's not something, it's something that happened a lot at the beginning of the universe and then sort of trickled down through time. And it's one of the things I really want to see with the James Webb Telescope. Can we see whether their galaxies come from black holes or vice versa? It looks like they form, there's something about the early galaxy forming that triggers the seed for the supermassive black hole, but we don't know for sure. We're just sort of, you know, do simulations at the minute. I really want to see observations of these.
Terrific. Well, I think perhaps we'll just sort of finish there on that question, which maybe get with James Webb, get a little bit closer to what the answer is of that question about black holes and galaxy formation. I'm just going to sort of wrap things up here, Carolyn, by thanking you so much for giving an excellent talk. The images, I have to tell you, were terrific on the screen here, and we could hear really clearly what you were explaining, and you did such a good job there, as if we yeah, we assume you would do because you're so good. But
well, thank you very much. Anyway,
and we're getting lots of comments in the chat as well, saying that what a good talk you've given, and also some nice images as well. So thank you so much. And yeah, so I'd just like to mention to everybody, just while you're online, that we'd like you to join us for upcoming events, which are hosted by our other nations and branches. The next talk from the Yorkshire branch was Vlatko Vedral, who's giving a talk which is No Sleep Till Schrödinger, which is 7 o'clock on, I believe it's the 20th of April, but you can check on the website for that. And if you wouldn't mind, everybody, there is a quick survey to fill in to tell us what you thought of tonight's talk and how everything was run. But yeah, just to say thank you once again from me to Carolyn for an awesome talk. Thank you, and have a good evening, everyone. Bye for now.